In the last video, we solved a differential equation that looked a little bit different than a linear differential equation in that the coefficient function in front of the differential was not 1, and the dependent variable y was not to the first power. And that was because, although it seemed that way looking at this equation, but when we put it in linear standard form, we notice that we have a coefficient function y squared, which does not satisfy this, and our dependent variable y is not to the first power. It is actually to the third power. But that's okay, because as long as the differential is still to the first power, we can use the Bernoulli equation. The Bernoulli equation is where you basically do a u substitution, and you'll end up getting a linear dE, and you solve for that linear dE, and then at the end you just do a back substitution. Since v was equal to y cubed is equal to whatever v was. Now, just like linear differential equations, we could still check our answer to make sure that we got it correct. I'm going to use the v variable instead of our y variable just because it's easier, but try it with the y variable. You'll still be able to check your solution. But we have a couple things to note. We were not given an initial value problem, so we don't know what c is. C is just some constant. So we can't solve it like how we solved the initial value problem for the linear differential equation in the previous video, by simply taking the derivative and you find your solution. We're going to have to do we're going to have to substitute. So we're going to check our answer by substituting. So let's go up and find our differential equation, our linear differential equation that we found by doing a v substitution. Okay, now I'm going to have to substitute v is equal to 6 squared 6x minus 1 plus let's do c e to the negative 6x. We just brought that e to the 6x up by making the exponent negative. But now, so we found a substitution for v. Now we need to find a substitution for dv dx. So taking the derivative of this, we're still left with the constant. And the derivative of all this good stuff is just simply 6. Then the derivative of this is c times negative 6 e to the negative 6x. So let's make this look a little bit prettier by saying this is negative 6c. Okay, so that looks good. Let's simplify it by canceling out this 6 and the 6 squared. So ultimately we're just left with this. And we can even simplify this to 1/2. So this is the derivative of v. So now we need to substitute. We're going to have something for dv over dx. We're going to have something for v. And it's going to be identical to 3x. Yeah. Let's double check. Yeah. So this was our linear differential equation that we found by doing a substitution. And now let's plug in what we have here. Then we're going to plug in what we have here. And it's pretty much just simplifying from here. Let's factor in this 6. We're left with 1/2 minus 6c e to the negative 6x plus 3 over 6, 6x minus 1 plus 6c e to the minus 6x is identical to 3x. And expect a lot of cancellations. This negative 6c to the e to the negative 6x, and this positive becomes 0. So we're left with 1/2 plus, now let's factor this in here. We're just left with 3x minus 3 over 6 is identical to 3x. This is just 1/2. This is positive 1/2. This is 3x. And I'm sure you're already seeing it now and getting really excited. These two equal 0. So 3x is identical to 3x. Therefore, our solution is correct. Now you could do it with y cubed, but notice how easy it was. From v, from our substitution right here, we just go backwards. So as long as we did all of this stuff correctly and got here, if we check our solution and it matches up and we create an identity, then turns out our solution to the differential equation using the Bernoulli theorem is correct.